Good evening, everyone. I am Krishnakant Dubey, a postdoctoral fellow, Department of Physics, IIT Bombay. I am going to present my work, Pressure-Driven Isostructural Phase Transition and its implication on Neal-Skyrmian host hexagonal PTM-NGS system. So this is outline of my presentation. First, I will discuss this Skyrmian, type of Skyrmian, just basic one. Importance of Skyrmians in spintronics, motivation of work, results, and further I will conclude my work. So a Skyrmian, first let me discuss. So a Skyrmian is basically a localized topologically protected spin texture in which magnetic moment rotate continuously from center to edge, forming a stable wheel-like configuration such as here it is shown. Depending on magnetic configuration, it is of basically three types. It can be more. First, a Neal-Skyrmian, block Skyrmian, and anti-Skyrmian. It can be more depending on this combination of two Skyrmian like bi-Skyrmian, tri-Skyrmian, Meron, bimeron, and so on. So in Neal-Skyrmian, the center in the Neal-Skyrmian, the center spin rotates along radial direction to the periphery of this Skyrmian, while in block Skyrmian, the center spin rotates tangentially around this Skyrmian, and in anti-Skyrmian, it is a mixture of both Neal and block Skyrmian. So this is basically this in importance in spintronics. The Skyrmian enables ultra-high storage density because of its low size, nano dimension, stable information storage because of non-trivial spin structure, reduced power consumption and fast data processing, and many more. So the challenges is basically towards its practical application because it needs to be stabilized at room temperature. So it has a problem with low temperature stability and narrow stability temperature window. So recently there is literature, one report on PTM-NGS system which shows that Neal-Skyrmian is stable in the broad temperature range from 5 Kelvin to 220 Kelvin, and it is more stable thermodynamically between 210 Kelvin to 20 Kelvin. So our aim is to stabilize the Skyrmian around the room temperature. So there are many ways to tune this Skyrmian to near room temperature. One is the pressure, mechanical strain. Other is by doping, changing the composition, apply these magnetic fields, apply the currents. So the pressure is more clean medium. So we focus on this pressure tuning mode. So there are a number of literature which suggests that by applying the pressure we can tune this Skyrmian to near room temperature or higher temperature. So one of the important property of this PTM-NGS system that if we increase the pressure, then there is increase in transition temperature. So the tuning parameter we can use pressure. So here from here we get the idea to use this pressure as a tuning parameter. This is the magnetization as a function of temperature of PTM-NGS system, where we can see that it undergo from paramagnetic to ferromagnetic state from here to here, and this in this highlighted region it undergoes spin reorientation transition. So this is region means here I am interested to study the pressure dependent effect. So this is the room temperature and 0 GPa pressure of this PTM-NGS system, which shows the fitting shows that it has a hexagonal structure with a space group P60 by MMC with this lattice parameter. So further we study this pressure dependent XRD data at room temperature at Electra beamline. And here we can see that as we increase the pressure from 0 to 14.5 GPa pressure, there is neither generation of new peak nor splitting of the peak, which suggests that the structure remains hexagonal throughout the pressure till 14.5 GPa pressure. Further we study this lattice parameter as a function of pressure. What we can observe here that the it deviates from linear behavior at around 6 GPa pressure. That indicates that this system undergoes a isostructural phase transition with pressure at room temperature. So to confirm this isostructural phase transition, we perform this. We use this BM equation of state on this volume as a function of pressure curve, and what we found that if we use single BM equation of state, we cannot fit this curve. So we have to use two BM equation of state to fit the curve, and both curve crosses at around 6.23 GPa pressure. So this also indicates the isostructural phase transition around 6 GPa pressure. Further, to confirm this, we linearize this equation, and we found that after the linearization there is a curve like a structure, means deviation starts from 6 GPa pressure. So that confirms that it has a isostructural phase transition. Further, we study this, we perform this temperature dependent structural analysis. This data has been taken on Petra beamline P021, and what we can observe here that if we decrease the temperature from room temperature to low temperature, there is only the temperature effect, means peak is shifting to higher angle with temperature, and there is neither generation of new peak and not a peak is splitting with the temperature. So here we can see that means there is a preserve hexagonal symmetry with temperature. So this is the fitting of high temperature, means room temperature and low temperature data, and this is fitted with P60 by MMC space group. So we plotted this lattice parameter as a function of temperature and volume as a function of temperature. What we can observe here that this deviation start at 210 Kelvin, and this 210 Kelvin temperature is in the thermodynamically stable Skyrmian region. So here from here this study performed at 0 GPa pressure, and we compare this lattice parameter as well as volume, and what we find that the volume at 21 Kelvin is almost equal to the volume of PTM-NGA at 1.09 GPa pressure. This suggests that if we apply this 1.90 GPa pressure, then this thermodynamically stable Skyrmian region, means which is around 210 to 220, it can be shifted to higher temperature or near room temperature.
You have 3 minutes.
Okay, ma'am, thank you. So these our experimental study also we have performed, our collaborator performed this theoretical calculation. This is DAS, where we can see the spin up. It changes rapidly, and at around 6 to 8 GPa pressure, there is a slightly slow variation of this density of state. We have also performed this electronic structure as a function of high symmetry point. So where we can also we have also observed that this our experimental verification means at below 6 GPa pressure there is a different electronic structure, and above 6 GPa there is different electronic structure. That means electron plays a role with the pressure. So after the reviewer comment, we perform this this simulation of Skyrmian using Ohm software, where we choose the region at 2 non-Skyrmian region, means which is around 250 Kelvin at 0 GPa pressure. What we found that if we simulate this result, means there is no Skyrmian. It is Skyrmian like structure, but central spinning is missing. So after application of this pressure, 0.6 GPa pressure, means we perform this magnetization measurement. This is the maximum pressure what we can achieve during the experiment. So we perform this simulation on this pressure only, and what we found that if we apply this 0.6 GPa pressure at 250 Kelvin, then there is a Skyrmian, stable Skyrmian. And we also calculated the topological charge, which suggests that if we apply this pressure on then the thermodynamically stable Skyrmian region can be shifted to higher temperature regime. So this is the conclusion of my work. This is a crystal structure remains preserved with pressure at least up to 14.5 GPa pressure, the maximum pressure what we can achieve during the experiment, and it shows this isostructural phase transition at 6 GPa pressure, and And after the simulation result, what we can conclude that after the application of the pressure, we can tune this thermodynamically stable equilibrium region to the higher temperature region. So thank you for your kind attention.
So with 14 gigapascal pressure you are applying, right?
Yes.
So it's quite significant. At that high pressure, I assume quite a lot of anharmonic effects will be there in your distortion. So it should not be linear or something like that.
Lattice parameter.
Yeah. So how much your lattice parameter in terms of percentage is changed?
So actually I have not calculated that one, but
Okay. Now I was just wondering that in one sense you are doing DAP.
but it is changing at 6 GPa pressure.
That's fine, but
Yes.
you have quite a lot of pressure. I mean, you have given into your supercell. So
Yes, yes.
with that amount of pressure, the potential energy surface is no longer a Born-Oppenheimer approximations valid. So it's more complicated. So you have to possibly do a full-fledged different types of methodology to capture that type of distortion. And that's what I was wondering.
Oh.
We have done any DFT, we have done only micromagnetic.
But
No, DFT has been done.
DFT you did
Yeah.
Yes, yes.
So that was my questions. Like why you are mixing
Then
this?
definitely,
Yeah.
No, DFT has been done, and this has been published in PRM recently.
And then this micromagnetic.
Yes, yes, yes. I have done it.
So this system is showing whatever. This system is showing this fermion under pressure.
Now, without pressure, it has a low means up to 220 Kelvin. But with pressure, we are claiming that means it would increase with pressure. Means at least 250 Kelvin. We have done simulation and we have found this fermion.
In bulk structures.
Yes, ma'am.
Bulk structures.
The question is like, in simulation you can do easily whatever you wish to do, to be very honest. Because if you run something, you will get some output. How those outputs are realistic in terms of predictive or real experiment, that's basically something to bother, right?
Yes.
So possibly that thing you can check whether it is.
Okay.
You can measure transport property. That should also indicate.
We were planned was
Right.
due to some region weak.
So very nice work and very nice presentation. So I have a doubt in your slide number 5. So there you had mentioned about this metastable fermions. So can you give a experimental perspective how we can stabilize the metastable fermions? Some of the possible ways experimentally how we can stabilize the metastable fermion. That's the question. Like slide number 5, you had mentioned about like around from 5 Kelvin to around 205 Kelvin around. You are having this metastable fermion.
Yes,
Yeah,
yes.
5 to 200 K metastable fermion is there. So how can we stabilize that? So metastable fermion means there is something which is above the ground state, right? So
Yes,
how
yes.
can we probe experimentally?
Experimentally, they have probed this. Means in this paper, they have probed using this LTEM technique.
No, that's how we measure. Like that's how we observe that.
Yes, yes.
Discuss because we have to run just talk to the speaker and then. So let us thank the speaker for a nice talk. And the next.
So, good evening, everyone. Am I audible?
Yeah, sure.
So, good evening. Here, the title of my talk is Ultramagnetism in Tetragonal CE-based Necktides, a post-principle investigation. So, myself, Dr. Narayan Nambudiri P. I am a postdoctoral fellow in SRM University in Quantum Transport Group, headed by Dr. Pankaj Bella. So, this work was done in collaboration with Dr. Tanay Nag, Bitspilan Hyderabad campus, and Dr. Banashree from Mahindra University. So this work was recently published in RSC Advances. So as the title suggests, we are dealing with the cerium-based necktides. So this rare earth cerium-based necktide, due to their partially filled 4f orbitals, will give a strong electronic correlation. So this among these tetragonal necktides, we are dealing with X2Y2 compound, and where the magnetism, spin orbit coupling and crystal symmetry leads to and this material leads to a good topological material. So here we focus on CE X2Y2, where X belongs iron, cobalt, nickel, and Y belongs phosphorus, arsenic, and antimony. So this in this structure, the CeCO2P2 was found to crystallize in the tetragonal THCr2Si2 type structure as proposed by Hugh et al. And here the CO atoms order antiferromagnetically, means the CO atom sitting at the CO atoms at the out of plane couple antiferromagnetically, and the current studies report CO based A type AFM ordering and chance of altermagnetism in CeCO2Y2. So coming to the motivation, we know that altermagnetism is a new phase of magnetic material where it shows both the properties of a ferromagnetic and antiferromagnetic material. So as like antiferromagnetic materials, they show zero net magnetic moment, but they show a momentum dependent spin splitting, and which is not arising from the magnetic moment of the atom. So this can generate spin polarized current without a stray field. So here our question is, does this emerge in the CO based CX2Y2 system? So recent first principle and experimental studies have shown that the CeCO2P2 hosts antiferromagnetic ordering combined with non-trivial band topology, and as proposed by Sakya et al., this CONB4SC8 exhibit A-type antiferromagnetic ordering where CO planes are ferromagnetically stacked and antiferromagnetically coupled along the C axis, and this CONB4SC8 behaves as an altermagnet. So despite this studies, the behavior of the system under atomic site substitution, as we are doing here, the transition metal substitution, and the effect of spin orbit coupling was not much explored in this type of material. So coming to the structure, here as I already mentioned, this crystallized in a tetragonal THCr2Si2 type structure, and here we can see the cobalt atoms, the in-plane cobalt atoms couple ferromagnetically and the out-of-plane couple antiferromagnetically, and here the cobalt atoms form a square lattice, so the effect of magnetic fluctuation can be avoided. Now here we have used the quantum espresso to simulate the electronic and magnetic properties, and here we have used GGA-PBE as the exchange correlation functional, and an energy convergence of 10⁻⁻7 eV was used, and we have included the Hubbard-U GGA plus U calculation also, and a K mesh of 12 × 12 × 8 was used for the calculation. So here we have done the calculation for both ferromagnetic as well as antiferromagnetic configuration for this transition metal sites, and we have found that this CO type structure crystallized in the antiferromagnetic, whereas the iron and nickel shows the ferromagnetic coupling. Now coming to the electronic structure, so here we can see that the flat bands are seen above the Fermi level, and these are the contribution from the localized 4f electron, and mainly the CO atoms are located below the Fermi level, and the degenerate overlapping spin up and spin down behavior shows the antiferromagnetic coupling of the cobalt atoms. So the density of state also we can see the same, and the sharp peaks in the conduction band, it shows the localized nature of the F electron, and here the symmetric dose in the valence band shows the antiferromagnetic coupling of the cobalt atoms. Now coming to the magnetic properties, the iron and nickel transition metal with the iron and nickel shows very weak magnetism, and the magnetic moment at the iron and nickel side was found to be 0, and the cobalt atoms show A-type AFM ordering with the cobalt atoms in plane coupled ferromagnetically, whereas the cobalt atom sitting at the alternate planes coupled antiferromagnetically, and as the nitrogen size increases, it weakens the 3dp hybridization, and it results in the more moment at the CO side. Now coming to the main part of the talk, the altermagnetic behavior. So we have plotted the band structure plot along different k path, and we have observed the momentum dependent spin splitting for the up and down spin for a value of 0.31 electron volt, and this Fermi surface show a 4-lobe structure which confirms the D-wave altermagnetic ordering for the CeCO2P2 structure. So now concluding the work, so we have confirmed from the DFT that the CEX2Y2 structure crystallized in the THCr2Si2 type structure with the cobalt based compounds hosted A type A for modeling, while the nickel and iron based compounds show weak magnetism. Now this CE4F states remain strongly localized near above EF, and the CO states occupy well below the Fermi level and couple antiferromagnetically along the C axis. And the CeCO2P2 exhibit a D-wave altermagnetism with a 0.31 electron volt momentum dependent spin splitting, which are driven by the symmetry rather than the magnetic moments. So finally, I would like to thank my research group. This is our QTG group in SRM University AP, and I thank SRM for giving me a postdoctoral position, and we are thankful to the ANRF for giving fund for establishing the computational facility, and finally I am thankful for the QMAT organizers for giving me an opportunity to present our work. Thank you.
Thank you. You are well in time. So, question.
So where the band structure, the gamma is shifted, is the band folding or just type? So your
This band structure?
this one. So your gamma and X little bit shifted in the left, right?
Oh, actually, sir, this plot was means actually only this 3 points were there. So this splitting was X gamma X. In that range, the splitting was happening.
Along the line, your gamma should be there, no? The gamma is.
Actually, this is the gamma.
Okay. You have written it wrong.
That is
Yes, sorry, the axis got. No, actually the band was shifted. So, sorry, it was a mistake from my side.
Let us thank the speaker. Nice talk.
Okay, so good evening everyone. I'm Pallavi and I'm a postdoc student at NPL. And this is my work from JNU, which I did during my PhD. So today I will be giving my presentation, a talk on this thing that is observation of inertia-driven relaxation dynamics in CO8ZN7 MN5. So firstly, what is magnetic relaxation dynamics? So that is like when we perturb a system with field, with a time-changing field. So the magnetization takes time to relax. So that is what we want to study. We want to see what are the physical mechanisms, how the spin dynamics change, and what are the hidden mechanisms we can find. So we have studied for this system because we want to know whether this material goes along with the conventional models that have already been predicted, or whether it shows some deviations. So that is why we have studied. So yeah, this is just an introduction to the magnetic relaxation dynamics, in which we perturb the system using an AC field, and then we measure the magnetization corresponding to that, and then we see with different frequencies how it is varying, and then we try to fit the models and see what parameters we can find and what mechanisms we can get. So firstly about the system, the CO8ZN7MN5, this is a chiral magnet, beta type chiral magnet. Actually this system has a broken inversion symmetry, and that is why it has competing magnetic interactions present. And due to this competing magnetic interactions, it hosts fermions as well as many different magnetic phases like helical, conical fermions. And in order to understand, and that is why we have selected this system for this study, and we have probed it near this fermion phase region to get the magnetic, understand the dynamics. So next I'll introduce the conventional models that we use to study this. So the first one is just a second. The first one is this Debye model which we use, where the magnetization tends to relax with exponentially with time. So generally in this model it is considered that the relaxation distribution in the relaxation time is 0. So there is one relaxation time and all the moments are relaxing with the same relaxation. And the other one are the Kole and this Havelock-Nagami models, which are just the extended Debye model, in which we use distribution parameters like alpha and beta in order to account for the distribution which is taking place, which is not there in the Debye model. So this is our data, the frequency dependent AC susceptibility data which we have taken for this chiral magnet. So as we can clearly see that over here, Over here, the frequency dependent behavior in the real and imaginary part of AC susceptibility, both of them are considerably changing with frequency, and this shows that the relaxation frequency of this system lies somewhere near the experimental range. So in order to understand the dynamics in the system, we have used those previous datas, this one and this one, with the frequency to fit it with the theoretically given models and to see what is the relaxation time and the distribution. So the first one is this Debye model, which has when we tried to understand this behavior with the Debye model, we found that the data didn't follow the Debye model completely, although the best thing which we found was that the relaxation distribution is 0, but it could not, the Debye model could not explain the data. So the next one is this Coley-Davidson model, which is again extended Debye model with the distribution in the relaxation time. And we can see that again, the distribution, that is the relaxation, distribution in the relaxation time, it dropped down to 0. That is, it came to Debye limit, but it could not explain the data. The next one is a Havelock-Nagami model, where again, this is also one extended model which takes additional parameters just to understand whether there is a distribution in relaxation time which could not be captured, but again, this failed. Again, giving the same parameters as the earlier ones, it is a Debye and the Coley-Davidson. Next, so we need to think that what models, new models can it follow, and if it follows, then what can be the hidden mechanisms in that system, or what are the physical mechanisms which is making it behave that way. So, so one model is the inertial relaxation model, which has been used in spin-ice systems, like in quantum spin-ice, where normally the quantum spin-ice follows the spin-ice rules and the spins are 2 in and 2 out configuration. So sometimes if we increase the temperature, flipping of spins can take place, and that can result in the formation of emergent monopoles and emergent monopoles over here. So just like in grid of bar magnets, and if we flip them, then we can see there is a concentration of concentrate north pole and south pole over there. So the propagation of these monopoles in this quantum spin-ice can result in these inertial effects. Similarly, in ferrofluids also, there can be this kind of inertial dynamics present due to the rotational inertia. And in order to understand whether this system also follows this model or not, and if it follows, then why, we did the fitting using the inertial fit. And we can clearly see that the data was completely could be understood, could be explained using this model. And one more thing was that the parameters that we got, they were in complete agreement with each other for the real and the imaginary part, which was not there when we did it for the earlier theoretical models, that is the Coley-Davidson, Debye and Havelock-Nagami. So over here, we tried to understand the physical interpretation, like if this system is showing this kind of behavior, then what could be the reason behind that? So the first question was that, does this system has monopoles? No, it does not have monopoles in the sense like in quantum spin-ice where there were emergent monopoles present. But over here, these systems host fermions. So just because it hosts fermions, sometimes in what happens in this when topological phase fermion is a topological phase, right? So whenever there is a creation or annihilation of fermion takes place to the phase transition, it is a topological phase transition, and during that topological phase transition, block points are formed, that is like monopoles or anti-monopoles, they behave like them. But if it would have been due to those, then we would have got only the inertial effect at the phase transitions of this fermion, not for the entire field range for helical, conical and fermion. So the next one is the domain wall. So it was that in domain wall sometimes also can show the inertial effect, like if we apply the AC field, the rocking back and forth of the domain wall's movement can show inertial effect. But and the measurement which we did was in fact in the domain wall region, that is there were domain walls, the saturation was not there, but still this can be a partial contribution because other systems also have domain walls, and such kind of systems like chiral magnets, they don't show this, so we are not sure about this thing. The next one is the fermion dynamics. So fermions also exhibit inertial like effects, but again if skyrmions would have been the reason, then the inertial effect would have dominated only in that phase, not for the entire field range. And so the most possible reason for now, we can say that there are spin fluctuations, because this system can host fast, like there are reports that it hosts very fast fluctuations, spin fluctuations are present. So we can say that, okay, the spin fluctuations can alter the magnetic response, and because spin fluctuations also can change the dynamics of the system, and they can alter the magnetic response to give this effect, but this is also a possible reason. So this is the conclusion. So first we studied the magnetization dynamics of CH, Zn, Mn5. We tried to see which model could be used to explain this data, and we found the observation of inertial effects, and the models which we used, like the inertial effect showed a good agreement with the parameters, and and we tried to qualitatively explain like what can be the reason behind this, but for that future measurements are also needed. So these are the references. The first one is our paper, which has been published in PRB. Thank you.
Question. So this is a particular system. You have done only AC susceptibility measurement here,
Yes,
right?
ma'am.
And then try to fit it with some model which is mimicking your non-linear response data.
And ma'am, one more thing which I didn't mention in this, we tried it for the other composition also from the same family, and it also behaved the same, it showed the same results. So we haven't put this in the PPT, but it is there in the paper.
So these are only, is there any
Only
static
just-
magnetization measurement also done?
Yes, ma'am, we have done the
Have you,
magnetization.
shown it?
So, ma'am, I haven't shown it over here because
Definitely, yeah. So
it's
that has
8-minute talk.
Yeah, spin fluctuation. And any other proof of this spin fluctuation?
No, ma'am. That is why I've said that it is a possible reason. We have to still figure it out. That
And
why
these are
is it emerging?
bulk system.
Bulk system.
By arc melting or?
No, ma'am. Solid state. Actually, we made the sample to melt growth technique. It could be assumed as a single crystal, but it is not because there are some grains present, large grains. So that is like poly.
Polycrystalline
Yeah.
material. Okay, thank you.